Jai Hind, welcome to class of Fundamentals of Electronics Engineering. This is the subject code. This is the first year subject. Here we'll be talking about why do we need to study electronics engineering, what are the basics, what are the fundamentals of electronics engineering. These are the topics that we cover in Unit 1, where we'll be talking about semiconductor diodes, depletion layer, VI characteristics, ideal and practical diodes, diode equivalent circuits, Zener diodes, the breakdown mechanism. There's so many things that we'll be covering in Unit 1. So let's start with the very first lecture, where we'll be talking about basics of semiconductor materials. First of all, we need to understand what are our semiconductor materials. As the name says, semiconductors. So we need to understand first of all what are conductors, what are insulators, and what are semiconductors. Conductors are basically the devices, the electronic equipments that allows electricity to pass through them, right? And insulators are a class of elements, class of devices that do not allow current to flow through them. Then if we talk about semiconductors, they usually behave as insulators, and in particular condition, they act as conductors. So they are semiconductors. What are the environmental condition that makes an insulator behave as a conductor? So we will be talking about all of that. So there are special class of elements that are semiconductor materials. The most famous ones are germanium, silicon, and gallium arsenide. So first of all, we need to understand what are semiconductors. Semiconductors are special class of elements having a conductivity between that of a good conductor and that of an insulator. So their conductivity is lying somewhere in between. They are not as good in conducting, passing electricity as conductors, and they are not as bad as insulators in resisting the current. So if you want to classify on the basis of what kind of crystal structure they are, if they are single crystal structure, we have examples like germanium and silicon. If we talk about compound semiconductors, we do have gallium arsenide, cadmium sulfide, gallium nitride, gallium arsenide phosphide, many more. The most famous ones are germanium, silicon, and gallium arsenide, right? Let's talk about little history of semiconductors. With the help of these semiconductors, we do make certain devices like diodes, transistors. What is a diode? Diode is a two-terminal device that allows flow of current in particular condition. The first diode was made using germanium in 1939. Then what are transistors? Transistors are mostly used as switches. It was first of all invented in 1947, and the first transistor was made using germanium. Then in 1954, silicon took over germanium in making transistors. Reason for it is silicon is less temperature sensitive and it is abundantly available. If an element's temperature sensitivity is less, the fluctuation in its parameters, whenever there is variation in temperature, will be lesser. So an element with lesser fluctuation, more stable behavior is preferred. So silicon is preferred over germanium, right? Another reason for using silicon over germanium is another reason for preferring silicon over germanium is its availability. It is abundantly available. So availability makes the cost lesser than less available material, right? So first of all diode, then transistor, both were made using germanium, then silicon took over. Then after, we used a compound to make those transistors, and which proved to be a better transistor. Better in what way? Better in terms of speed. If I'm using a transistor as a switch, I would prefer a faster switch. So when I use gallium arsenide instead of silicon in transistor, it proves to be a faster switch as compared to silicon, So these three are the semiconductors of choice. Germanium was first discovered. It was used in 1939 as a diode and as a transistor in 1947. It is too sensitive to temperature changes, so it suffers reliability problem because of its higher temperature sensitivity. Silicon was introduced in 1954. It was used as transistor. It is less sensitive to temperature. It is abundantly available. Over the time, it's sensitive to issue of speed. So gallium arsenide took over in 1970s. We made transistors. It has 5 times faster speed. But we have certain limitations, like it is difficult to manufacture transistors using gallium arsenide, and it is little more expensive as well. It has little design support at early stage, complexity, right? Now let's talk about how silicon and germanium act as semiconductors. Now if I talk about the atomic structure of silicon, silicon has atomic number 14, so its electronic configuration will be 284. So in the outermost shell or in the valence band, it has 4 electrons. You can see it from here. This is the nucleus. In the first layer, it has 2 electrons. In the next, it has 8. 1, 2, 3. And in the outermost shell, that is valence band, it has 4 electrons. 1, 2, 3, 4. Right? So 14 orbiting electrons it has. These 4 electrons are present in the valence band. If they are excited enough to jump to the conduction band, they'll act as free electrons and they will help in conduction of current. So let's understand the theory behind flow of electrons and conduction of current. Whenever electrons are moving with variable velocity, like if electrons are generated, we know that electrons are generated from the cathode terminal and they move towards the anode terminal, that is positive terminal, right? So their speed can be varied. If I increase the positive potential at the anode, electrons will move faster, they will be accelerated. If I decrease the potential at positive end or the anode, their speed will be reduced or they will be deaccelerated. This variation in velocity and the movement of electrons will generate current. If electrons are moving from cathode to anode, there will be flow of current from anode to cathode. And where do we get these free electrons? Are these available in the conduction band? If not, they must be available in the valence band. Then we need to apply some external force, some external energy that will enable the electrons to jump off from valence band to conduction band. Now what are valence band and conduction band? That I am going to take next. So we can see here silicon has 4 electrons in the valence shell. If I talk about germanium, has 32 atomic number, 32 electrons total. So it will be 2, 8, 18 and 4. Again it has 4 electrons in the outermost shell, right? Now let's talk about gallium and arsenic. Gallium has 3 electrons in the outermost shell, so it can be called as a trivalent. Silicon and germanium are tetravalent. Gallium is trivalent. And arsenic is pentavalent. Pentavalent in a way that it has 5 electrons in its outermost shell or valence band, right? Now let's see, whenever it is the formation of bond, that depends on whether ionic bonds are formed or covalent bonds are formed. Ionic bond is formed whenever we are donating or accepting electrons, whereas covalent bond is formed whenever we are sharing electrons to complete the outermost octet. Let's talk about silicon. Silicon forms a crystalline structure when one atom of silicon makes a bond with another atom in a way that their outermost 4 electrons share the outermost octet and complete the outermost octet. One silicon has 4 electrons in the outermost shell, another silicon atom also has 4 electrons in the outermost shell. When they do the sharing thing, their outermost their valence electron is complete, their octet is complete. There are 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Like this is called as covalent bond formation that is done with the help of sharing of electrons. This bonding of atoms strengthened by the sharing of electrons is called as covalent bonding. Now let's talk about gallium and arsenic. Now as we see that gallium has 3 electrons in the outermost shell and arsenic has 5 electrons. 5 plus 3 will also make 8. So they can also form covalent bond, and the crystalline structure of GaAs will be somewhat like this, where gallium will be sharing its 3 electrons and arsenic will be sharing its 5 electrons. We can see arsenic has these 1, 2, 3, 4, 5. These 5 electrons are shared by arsenic, whereas it is shared by this gallium is giving its 3 electrons in the outermost shell and it is completing the octet. There is sharing of electrons, 5 electrons provided by arsenic and 3 by gallium atom, and the outermost octet is complete. Now let's talk about energy bands. What are energy bands? Energy bands and band gap are two different terms. We need to understand this very clearly. In solids, the electron in the same orbit have a range of energies rather than single energy. Similar is the case of frequencies. Whenever we communicate, we do not communicate using a single frequency. We are assigned with a band of frequencies, right? So when we are assigned with a band of frequency and we do communication, similar way we can understand this. That is, the electrons does not lie on single energy level. There is a band. Complete band means range of energy, right? So I would represent it with, this is a complete band. So if I have to represent my valence band, I would represent it like this. If I have to represent my conduction band, I'll represent it like this, and I'll keep some band gap between the valence band and conduction band. Usually whenever bonding crystalline structure is made like of silicon and gallium arsenide, their outermost electrons are present in the valence band, but whenever they are excited, they are provided with biasing or external energy that will help these electrons to cross this band gap and jump off to conduction band, then they are free for conduction of current. So we need to understand what is energy band. In solids, the electrons in the same orbits have a range of energies. What does it mean? All the electrons present in valence band will possess similar energy rather than a single energy. They have a range of energies. This is called as energy band. This is the definition of energy band. The closely placed energy levels, which differ slightly in energy, therefore form an energy band, right? So this is an energy band, valence band. This is an energy band, conduction band. The energy band which possesses the valence electrons is called as valence band, and the energy band which possesses the conduction band electrons is called as conduction band. Conduction band is next higher level energy band level. The energy band which possesses the free electrons is called as conduction band. Electron in this band take part in conduction. If an atom has empty conduction band, it means there will be no conduction of energy. If we have all the electrons here in the valence band and no electrons in the conduction band, then we do not have free electrons for the movement, for the flow of current. Now we understood what are energy band. Now what is forbidden energy gap? Like this is one energy band, this is another energy band, like this is valence band, suppose this is conduction band, and the band gap between two energy bands is called as forbidden energy gap. It is a region in which no electrons can stay. As the name suggests, forbidden. Electrons cannot stay here. It is forbidden because there is no allowed energy state. Either the electrons have to be in valence band or the electrons have to be in conduction band. If they have lesser energy, they'll stay in valence band. If they're excited enough, they'll jump from here to conduction band. If that energy is not that sufficient that they'll jump from valence band to conduction band, they'll return back to valence band, but they'll not stay here. So this is the forbidden gap. For silicon, it is a fixed value which is approximately 1.12 electron volt. We need to specify the units always, right? And for germanium, it is 0.72 electron volt. So between valence band and conduction band, there is an energy gap. So we may call it energy gap, written as E subscript G, which is also called as forbidden energy gap. This is also called as forbidden energy gap. So either we call it energy gap or forbidden energy gap. If we provide less energy than Eg, the electron will not be lifted because there is no other energy level between valence band and the conduction band. They will not be lifted, right? So whenever we need to excite them, we need to send them to valence band, we need to provide energy higher than Eg. We all are aware by this diagram. We have studied in our school in physics. After nucleus, there is third level, the second level, valence level. So energy gaps between these levels is represented here, right? Innermost shell and valence band is the outermost shell. The farther an electron is from the nucleus, higher is its energy state. True. Like conduction band electrons have higher energy as compared to valence band electrons. Now we'll see energy levels and band gap for conductors, semiconductors and insulators. Let's talk about insulators first. I am representing here the valence band and the conduction band. These are two energy bands which is represented by the shaded blue region. This lower shaded blue region represents valence band. This is complete range of energy, right? Electrons in my outermost shell are present here. And in conduction band of insulators, there are no free electrons. As we know that insulators do not conduct electricity. They are bad conductors of electricity. They are the insulators. In such case, I have to represent the forbidden energy gap or the energy gap with a broader distance. Here, the forbidden energy gap represented by Eg must be greater than 5 electron volt. It is always greater than 5 electron volt, which is a high value. So, usually the electrons are unable to cross this band gap and reach the conduction band, right? Even if they try, they'll come back and settle down here. These are the valence electrons which are bound to the atomic structure. Now let's talk about conductors. In conductors, this conductors means they are good conductors of electricity. There is always flow of current. They do not resist current. What does that mean? That means there are always free electrons present in the conduction band. In such case, we consider the electrons present in the valence band are only available for conduction of electricity. In such case, my valence band and conduction band are overlapping. When my valence band and conduction band are overlapping, these two lighter blue shades where in the middle is that overlapping region is shown by a little darker blue shade. Can you see that? And we have represented with negative charge the electrons here. Here also with the negative charge we are showing electrons here. So in insulators the band gap is too high, in conductors it is overlapping. What is the case of semiconductors? In semiconductors the band gap must be lesser than insulator, but it should not be overlapping. So let's see. Here is the valence band, here is the conduction band, and I have shown it with smaller band gap as compared to insulators. So how much is this band gap for a germanium crystal? For germanium it is approximately 0.7. For silicon it is approximately 1.1. But if we talk about compound semiconductor gallium arsenide, it is close to 1.43 electron volt, right? Hence, here there lies the possibility to provide such amount of external energy to enable our electrons to jump from valence band to conduction band. An electron in the valence band of silicon must absorb more energy than one in the valence band of the germanium. True? So, we need lesser energy in case of germanium to enable our electrons to reach conduction band. Whereas in case of silicon, we need a little higher energy and here a little more. To become a free carrier, free carriers are the free electrons due to external causes such as applied electric field, which is called as biasing, which we'll study later, by voltage sources or potential difference. Now, next subtopic, what are n-type materials, what are p-type materials? Now, so far we have talked about what are our semiconductors and what are the elements that we use as semiconductors. Most famous ones are silicon, germanium and gallium arsenide. Now, the question is what kind of materials we are talking about. If you want to classify it on the basis of type of free charge carriers, the classification is n-type and p-type material. Now, what is an n-type material? An n-type material is created by adding elements with 5 valence electrons such as antimony, arsenic and phosphorus. We are talking in terms of silicon. Now, we know that silicon has 4 electrons in its valence shell. To complete the octet, it needs 4 other electrons. But if another element has again just 4 electrons in the outermost shell, making the covalent bond, the octet is complete. Again, we are left with no free electrons, no free charge carrier. So, if we dope it, if we add some impurity of elements like antimony, arsenic or phosphorus, which usually have 5 electrons in their outermost shell, 4 will help in making the covalent bond and there will be 1 electron with every atom added. That will act as free electron for the conduction of current. So, when to a silicon crystal we add some impurities of antimony, arsenic and phosphorus, with every atom there is 1 free electron, and by increasing the doping, by increasing what is doping? The method of adding impurities. And if we add impurity which has 5 valence electrons, then such kind of material that will be formed is called as n-type material. What is a p-type material? If we are adding impurity that has only 3 electrons in the outermost shell, then deficiency of electrons will be represented by positive charge, which can be called as donor atom. So, antimony acts as a donor atom. So, either we can create n-type material or p-type material. In this case, it will be called as n-type material here when the free charge carriers are donor when we are adding donor atom, then this is called as p-type material. In n-type material, what happens? Here is the valence band, here is the conduction band, e.g. Now, here I have used a term intrinsic material. What are intrinsic material? The semiconductor material, pure silicon is intrinsic. When we add impurity to it, it becomes extrinsic, right? And doping is the process of adding impurities. So, for an intrinsic material, jumping of electrons, usually electrons occurs, right, from valence band to conduction band. E.g. is considerably less, right? The free electrons due to the added atoms have higher energy levels and require less energy to move to the conduction band. True? What are p-type materials? So far we have discussed n-type material, right? These are the materials which can be used as impurity to be added to silicon to make n-type material. Now, if I talk about p-type material, p-type materials are created by adding atoms with 3 valence electrons such as boron, gallium and indium. What will happen here? In case of insufficient, these are added to silicon. In case of insufficient number of electrons to complete the covalent bond, there will be a hole available. for the electron. Absence of electron, that is positive charge. It is represented by small circle, right? This can be represented by small circle, a void, right? Or plus sign indicating the absence of negative charge. The atoms are called as acceptor atoms here. So in N-type material, atoms are called as donor, and P-type material, these atoms are called as acceptor atoms, as they are capable of accepting one electron. We again check the picture for N-type. N-type, we have fifth electron which is available to be donated. So these are called as donor atoms. Here in P-type, this is deficient. Here, absence of electrons. So it can accept electron. So this is acceptor type impurity. Boron is an acceptor type of impurity, whereas antimony is a donor kind of impurity, donor atom. With the outwards arrow, I am showing it is capable of donating, and P-type, it is capable of accepting. Further, the topics include majority minority carriers, PN junction diodes, its working, which we will be covering in the next lecture. The operating conditions of diode is also, that is what we have to cover. These are the references that I have used for today's presentation. Thank you so much.